后我们的那个，简单来说，我今天架设一个神经网络，我应该要就是输入一个，比如说我左边的这张习惯的兔子，我输入之后，我希望它产生的结果是，它会认为这一张兔子要像你的拉斯凯。然后我自己也觉得说，这张绝对是你的拉斯凯，不会是张兔子啊，对不对？那结果这应该是我要产生的结果。那结果后来它产生的结果是认为说，哦，这一个是比较像一只兔子，所以它是一个不正确的结果。好，那么这个时候因为结果是错的，那这时候我们要做一件事情是说，它会做反向传播的一个修正权重。那这个时候这时候就要知道，就是说，反向传播法它是一个基于微分的一些实验室运算。那如果各位有兴趣的话，可以再去看一下它的东西。那我这边就把它再展开来跟各位介绍。各位可以知道说，它今天整个在运行的时候，它是那个修正，先去做一次的是训练，做一次的那个学习。学习完之后，他根据结果再去修正他的权重。那你们各位可以这样，那我这边有稍微画一个图让各位去看。那中间我左边这个是一个学生在学习，中间可能在做一个考试。好，这边有上过去。那考试完之后，他可能会产生一个结果。通常第一次训练完结果一定是7场1，比如这个 F 加，我记得美国 F 加好像是还是不行，我有点忘记。就是它这个叫做分数非常惨的意思。那这个时候我们应该是要重新的学习，然后去产生一个很好的结果。那这个是我们一个简单学习的目的跟它的流程。那这个时候我要跟各位讲说，因为我这边画的图啊。因为我们一个神经元跟神经元之间，它是由无数的神经网络有很多神经元不断的叠加、累加形成的。那它因为各位可以知道说，你每一个神经元它都会衔接到很多的神经元，那它的运算量跟幅度很大。那以过往的 CPU 的一个架构，其实你要去负荷这个神经网络的运算，是有一点困难的。所以这时候我们的 GPU 就是我觉得某种意义上也是一个关键的问题，也是有点跟他们商人有合并，所以可能在这一次起来之后，大家 GPU 怎么去买，其实 NVIDIA 是一个大众，就会看到。那近期的一些比较有趣的新闻是有讲到说，我们的 AMD 好像有点要重返荣耀，他们的 GPU 也出来，但是效能怎么样我还没有去看。根据一些新闻报道 ，AMD 那个整个 GPU 的效能不错，然后再加上它对于整个神经网络的一些嫁接，要让它的一些程式的那个封包都做来都还不错，所以我觉得如果各位有想要真的玩看一些神经网络的话，也可以用看 AMD 的显卡。不过我目前也直接NVIDIA，因为毕竟比较大众，而且我这边要偷偷跟各位讲 ，NVIDIA 它本身自己做的关于深度学习的一些算是驱动程式吧，都做得很完整。比如说各位可听过的CUDA，然后还有一个叫做 CUDA， 展开来说就是 CUDA for 深度学习，或者深度神经网络。那其实我这边简单的跟各位讲说，为什么 GPU 速度快？因为 GPU 本身是多线程的运算，就是我今天在 GPU 可能在运算的话，你就是资料塞进去，然后一个排队，然后一个处理掉。 但是 GPU 的话是你是开好几个专柜，让大家排队来多个运算把它处理掉。简单来讲是这样。所以为什么 GPU 好？那就是这个。那依我目前整个测试的速度，大概是差在7倍到8倍。那目前我们这个教室这些机台的一些效能，我还没有办法让各位直接去运行神经深度学习这样。那晚点说不定我把它 bug 掉，或者体验一下说什么是真的用 CPU 跑跟 GPU 跑上面的差异，其实还差蛮多的。那这边其实我有找几个不错的一个片点，那可以给各位看一下。因为其实，我刚刚有提到关于说，第一个影片是那个一个外国，算是外国的频道，他把神经网络的图画的很漂亮。我讲一讲。很多的那个网页啊，网站都会使用这一个 YouTuber 本身自己制作的影片去做解说、做 GI。它有一段，大概在这一段，因为你看到说中间这一个是一个相对比较复杂的神经网络，那左上角，它这边是在做一个图片分类。那他把左边的这一张左上角这张，把它丢到去
rendered at an extremely low resolution, 28 by 28 pixels. But your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My own is just that you come away feeling like the structure itself is motivated. The status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants. But in these 2 pixels of the input image, which is 700, is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing a digit. The activation here is, again, some number that's being inserted, or how trained it works.
那运算出来它会每个神经元会有一个相对，如果是比较位高的权重来讲，那这个高的权重如果一直保留到最后，它如果做分类来讲，它会产生一个最后那个最亮，它所谓最亮就是权重最高的那个神经元，就是代表它的强。就是可能最有可能是这个类结果。那这边是简单来讲是做分类，那当然也有分类。不过其实在整个神经元运算，它最后的差距是差在输出的那个激活函数上的差距。那我等一下会就是上礼拜那个我再跟各位讲一下说一些激活函数的差别跟用法，但我不会讲到太多数学式。因为讲到数学是会太复杂。那这时候我要拿另外一个，我个人在网络上看到我觉得蛮有趣的影片。这边可解释的人工智慧，这个是无意间看到的。那这个东西是什么？它里面也有稍微查到的。 这里可以大家看到什么？重点就一句话，科技是的 AI。是啊，所以对台也在时代上的话。那其实我这边讲来讲去，我觉得曾经所谓的生态实体 AI，我觉得都大家还是会回到一个议题啊，虽然说有点头脑的，就是大家会觉得说能不能取代人类这件事情，但我会觉得他没有办法真的实时的去取代人类，他只能去协助或帮助人类。那它很多的一些所谓的标记啊，或者是在取资料部分，还是得依照一些老经验，所谓的专家去做一个所谓资料写作的部分。所以这时候我还是得跟各位讲说，我们的 AI 可能跟各位讲，真的不太一样。那我们这边休息一下，休息个1分钟，那来。现在不能这样。
不用一直去提供，他回购不了什么牌子。
好，那个我们力轩继续准备一下，因为他发现他的这个系统上有一些小问题。来，我们来谈这个 Microsoft 有人工智慧方面的应用。我把各位接过来。好，待会哈，各位照我的做法，你输入 Microsoft 在 Google Search 里面。你输入这个 Microsoft Azure 就是 Microsoft 云端，然后AI 的链，你第一个搜寻到的应该是这个网人链 API 的链接端。那点进去之后呢，那各位可以看一看，就是说，它会在这边可以选择适用两步的一些政策，这是 Azure Microsoft Azure 的功能的一些技术啊。那我们现在看一下，待会要请各位去点这个适用人流链接，它可以给各位7天的人流链接的。
Of course, that just kicks the problem down the road because how would you recognize these subcomponents and what the right subcomponents should be? And I still haven't even talked about Microsoft influences the next, but run with me on this one for a moment. Recognizing Microsoft can also break down into subcomponents. One reasonable way to do this would be to first recognize the edges that make it up. Similarly, along the lines like the device the digits 1, 4, or 7, that's really just a long head, or maybe you think of it as a certain pattern of several So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when it looks like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with and those light up the neurons associated with the neuron. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be even useful for other recognition tasks. And even beyond image recognition, there are all sorts of intelligent things that break down into layers of abstraction. Parsing speech, processing raw audio, distinct sounds, which combine to make sentences, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the goal is to have some mechanism that conceivably combine pixels into edges or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neurons and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights, the switches that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then, the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like negative 10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that was fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposely tweaking the numbers so that the second layer picks up on the third layer picks up on etc. I personally find this satisfying rather than just treating the network as a total black box. Because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually do, you have a starting point for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra. So for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. And then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and a sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing was really doing. Now is the point I suppose I should say subscribe to stay notified about when that video or any new videos come out. But realistically, most of you don't actually receive notifications from YouTube, do you? Maybe more honestly, I should say subscribe so that the neural networks that underlie YouTube's recommendation algorithm are primed to believe that you want to see content on this channel get recommended to you. Anyway, stay posted for more. Thank you very much to everyone supporting these videos on Patreon. I've been a little slow to progress in the probability series this summer, but I'm jumping back into it after this project, so patrons, you can look out for updates there. To close things off here, I have with me Leisha Lee, who did her PhD work on the theoretical side of deep learning, and who currently works at a venture capital firm called Amplify Partners, who kindly provided some of the funding for this video. So, Leisha, one thing I think we should quickly bring up is this sigmoid function. As I understand it, early networks use this to squish the relevant weighted sum into that interval between 0 and 1, you know, kind of motivated by this biological analogy of neurons either being inactive or active.
Exactly.
But relatively few modern networks actually use sigmoid anymore.
Yeah.
That's kind of old school, right?
Yeah, or rather, ReLU seems to be much easier to train.
And ReLU stands for rectified linear unit.
Yes, it's this kind of function where you're just taking a max of 0 and a, where a is given by what you were explaining in the video. And what this was sort of motivated from, I think, was partially by a biological analogy with how neurons would either be activated or not. And so if it passes a certain threshold, it would be the identity function. But if it did not, then it would just not be activated, so it'd be 0. So it's kind of a simplification. So sigmoids didn't have training, or it was very difficult to train at some point, and people just tried ReLU, and it happened to work very well for incredibly deep
All right, thank you. For background, Amplify Partners, an early-stage VC, invests in technical founders building the next generation of companies focused on the applications of AI. If you or someone that you know has ever thought about starting a company someday, or if you're working on the real estate market right now, the Amplify folks would love to hear from you. They even set up a specific email for this video, 3blueonebrown@amplifypartners.com, so feel free to reach out to them through that.
那这边你可以选择不同的照片，然后会告诉你它的状况。各位可以尝试的从那个网络里面，假设各位你的照片放在云端的话，你把云端的照片，待会我自己偷偷做，我给你们看。我把我自己的照片放上来，看看他觉得我几岁了。65岁。哦，不是。看那个到时候那个电脑还在不在的，不知道他想的好不好。哎，这是什么？这是手表。
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more into how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in each layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer, plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of 2 hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. And what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure is that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be. And it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before.
除了这些之外它那时候呼叫 API 所以你可以在程式里面程式码里面得到它的结果之外。
Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MDIS database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, it feels a lot less like some crazy sci-fi premise, a lot more like, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function.
它这边如果是免费试用的话是 大概2年，因为我记得还是给3000多块，
and the weights in the weighted sum defining its activation are kind of like the strengths of those connections. The bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a tree, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer. That output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is a measure for how lousy the network is and how bad the computer should feel. That's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that. It takes as its input those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are. And the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. Just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as input and one number as output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of this situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative. If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill. And notice, even for this really simplified single input function, there are many possible valleys that you might land in, depending on which random input you start at. And there's no guarantee that the local minimum you land in is going to be the smallest possible value of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller. And that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with two inputs and one output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now, instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with 2 inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us 2 things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with 2 variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second variable. That at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. Alright, let's zoom out and sum up where we are so far. The network itself is this function with 784 inputs and 10 outputs, defined in terms of all of these weighted sums. The cost function is a layer of complexity on top of that. It takes the 13,000 weights and biases as inputs and spits out a single measure of lousiness based on the training examples. And the gradient of the cost function is one more layer of complexity still. It tells us what nudges to all of these weights and biases cause the fastest change to the value of the cost function, which you might interpret as saying which changes to which weights matter the most. So, when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Well, the one that I've described here, with the 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, well, it's not bad. It classifies about 96% of the new images that it sees correctly. And honestly, if you look at some of the examples that it messes up on, you kind of feel compelled to cut it a little slack. Now, if you play around with the hidden layer structure and make a couple tweaks, you can get this up to 98%. And that's pretty good. It's not the best. You can certainly get better performance by getting more sophisticated than this plain vanilla network, but given how daunting the initial task is, I just think there's something incredible about any network doing this well on images that it's never seen before, given that we never specifically told it what patterns to look for. Originally, the way that I motivated this structure was by describing a hope that we might have. That the second layer might pick up on little edges, that the third layer would piece together those edges to recognize loops and longer lines, and that those might be pieced together to recognize digits. So, is this what our network is actually doing? Well, for this one at least, not at all. Remember how last video we looked at how the weights of the connections from all of the neurons in the first layer to a given neuron in the second layer can be visualized as a given pixel pattern that second layer neuron is picking up on? Well, when we actually do that for the weights associated with these transitions from the first layer to the next, instead of picking up on isolated little edges here and there, they look, well, almost random, just with some very loose patterns in the middle there. It would seem that in the unfathomably large 13,000 dimensional space of possible weights and biases, our network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on the patterns that we might have hoped for. And to really drive this point home, watch what happens when you input a random image. If the system was smart, you might expect it to either feel uncertain, maybe not really activating any of those 10 output neurons or activating them all evenly. But instead, it confidently gives you some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. Phrased differently, even if this network can recognize digits pretty well, it has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined, unmoving digits centered in a tiny grid. And its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So with this as the image of what those second layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how you learn, that'll only happen if you engage actively with the material here somehow. One pretty simple thing that I want you to do is just pause right now and think deeply for a moment about what changes you might make to this system and how it perceives images if you wanted it to better pick up on things like edges and patterns. But better than that, to actually engage with the material, I highly recommend the book by Michael Nielsen on deep learning and neural networks. In it, you can find the code and the data to download and play with for this exact example. And the book will walk you through step by step what that code is doing. What's awesome is that this book is free and publicly available. So if you do get something out of it, consider joining me in making a donation towards Nielsen's efforts. I've also linked a couple other resources that I like a lot in the description, including the phenomenal and beautiful blog post by Chris Olah and the articles in Distill. To close things off here for the last few minutes, I want to jump back into a snippet of the interview that I had with Leisha Lee. You might remember her from the last video. She did her PhD work in deep learning. And in this little snippet, she talks about 2 recent papers that really dig into how some of the more modern image recognition networks are actually learning. Just to set up where we were in the conversation, the first paper took one of these particularly deep neural networks that's really good at image recognition. And instead of training it on a properly labeled dataset, it shuffled all of the labels around before training it. Obviously, the testing accuracy here was going to be no better than random, since everything's just randomly labeled. But it was still able to achieve the same training accuracy as you would on a properly labeled dataset. Basically, the millions of weights for this particular network were enough for it to just memorize the random data, which kind of raises the question for whether minimizing this cost function actually corresponds to any sort of structure in the image, or is it just, memorization?
Memorize the entire data set of what the correct classification is. And so a couple of, half a year later at ICML this year, There was not exactly rebuttal paper, but paper that addressed some aspects of like, hey, actually these networks are doing something a little bit smarter than that. If you look at that accuracy curve, if you were just training on a random data set, that curve sort of went down very, very slowly in almost kind of a linear fashion. So you're really struggling to find that local minima of possible, the right weights that would get you that accuracy. Whereas if you're actually training on a structured data set, one that has the right labels, you fiddle around a little bit in the beginning, but then you kind of dropped very fast to get to that accuracy level. And so in some sense, it was easier to find that local maxima. And so what was also interesting about that is it brings into light another paper from actually a couple of years ago, which has a lot more simplifications about the network layers, but one of the results was saying how if you look at the optimization landscape, the local minima that these networks tend to learn are actually of equal quality. So in some sense, if your data set is structured, you should be able to find that much more easily.
My thanks, as always, to those of you supporting on Patreon. I've said before just what a game changer Patreon is, but these videos really would not be possible without you. I also want to give a special thanks to the VC firm Amplify Partners and their support of these initial videos in the series. They focus on very early stage machine learning and AI companies, and I feel pretty confident in the probabilities that some of you watching this, and even more likely some of the people that you know, are right now in the early stages of getting such a company off the ground. And the Amplify folks would love to hear from any such founders. And they even set up an email address just for this video that you can reach out to them through, 3blue1brown@amplifypartners.com. Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons. And I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe, and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost. And that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a tube. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random. Maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations. We only have influence on the weights and biases. But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we wanted to classify the image as a tube, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down. We care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a tube get more strongly linked to those firing when thinking about a tube. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron was positively got brighter, and if everything connected to that digit 2 neuron would become more. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence this information, so we only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons of what should happen to this second to last layer, again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. Once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just a single training example wishes to nudge each one of those weights and biases. If we only listen to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow. So instead, you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need, whether that's having people label tens of thousands of images or whatever other data type you might be dealing with. And this actually transitions really nicely to today's extremely relevant sponsor, Crowdflower, which is a software platform where data scientists and machine learning teams can create training data. They allow you to upload text or audio or image data and have it annotated by real people. You may have heard of the human-in-the-loop approach before, and this is essentially what we're talking about here, leveraging human intelligence to train machine intelligence. They employ a whole bunch of pretty smart quality control mechanisms to keep the data clean and accurate, and they've helped to train, test, and tune thousands of data and AI projects. And what's most fun, there's actually a free t-shirt in this for you guys. If you go to 3b1b.co/crowdflower or follow the link on screen and in the description, you can create a free account and run a project, and they'll send you a free shirt once you've done the job. And the shirt's actually pretty cool. I quite like it. So thanks to Crowdflower for supporting this video, and thank you also to everyone on Patreon helping support these videos. The hard assumption here is that you've watched part 3, giving an intuitive walkthrough of the backpropagation algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the mantra to regularly pause and ponder certainly applies as much here as anywhere else. Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of networks, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is AL-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is Y. For example, Y might be 0 or 1. So the cost of this simple network for a single training example is AL minus Y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function. It's actually for us to give a special like C. This is a lot of terms, and the way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with the constant lets us compute cost. Of course, AL-1 is influenced by its own bias and such, but we're not going to focus on that. Now all of these are just numbers, right? And it can be nice to think of each one as having its own little number. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resultant nudge to the cost is. what we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of the tiny change to ZL to this tiny change W. That is the derivative of ZL with respect to WL. Likewise, we then consider the ratio of the change to AL to the tiny change ZL cost, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the change. We're multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's a lot of samples. So just make sure it's clear what they all are. Of C with respect to AL works out to be AL minus Y. Notice, this means that its size is proportional to the difference between the network's output and the thing that you want. So if that output was very different, then slight changes stand to have a big impact on the final product. The derivative of AL with respect to ZL is just the derivative of our signal function, or whatever nonlinear you choose to use. The derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now, I don't know about you, but I think it's easy to get stuck head down in the formulas without being able to sit back and remind yourself of what they all actually are. In the case of this last derivative, the amount that small nudge to the right influence the last line depends on how strong the previous neuron is. Remember, this is where that neurons that fire together all of this is the derivative with respect to WL, only the cost for a specific single function. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del Z del W term for a del Z del B. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of Z to the previous activation, comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating this same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L minus 1, and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like Z, so that the activation of the last layer is just your special function, like the sigmoid, applied to Z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case. It's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer L-1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is, on the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function, and you have to add those up. And that, well, that's pretty much it. Once you know how sensitive the cost function is to the activations in this second to last layer, you can just repeat the process for all the weights and biases feeding into that layer. So pat yourself on the back. If all of this makes sense, you have now looked deep into the heart of backpropagation, the workhorse behind how neural networks learn. These chain rule expressions give you the derivatives that determine each component in the gradient that helps minimize the cost of the network by repeatedly stepping downhill. If you sit back and think about all that, this is a lot of layers of complexity to wrap your mind around. So don't worry if it takes time for your mind to digest it.
Welcome everyone to 2019. It's really good to see everybody here, make it in the cold. This is 6S094, Deep Learning for Self-Driving Cars. It is part of a series of courses on deep learning that we're running throughout this month. The website that you can get all the content, the videos, the lectures, and the code is deeplearning.mit.edu. The videos and slides will be made available there, along with a GitHub repository that's accompanying the course. Assignments for registered students will be emailed later on in the week. And you can always contact us with questions, concerns, comments at HCAI, Human-Centered AI, at MIT.edu. So let's start through the basics, the fundamentals. To summarize in one slide, what is deep learning? It is a way to extract useful patterns from data in an automated way with as little human effort involved as possible, hence the automated. How, the fundamental aspect that we'll talk about a lot, is the optimization of neural networks. The practical nature that we'll provide through the code and so on is that there's libraries that make it accessible and easy to do some of the most powerful things in deep learning using Python, TensorFlow, and friends. The hard part always with machine learning and artificial intelligence in general is asking good questions and getting good data. A lot of times the exciting aspects of what's the news covers and a lot of the exciting aspects of what is published in the prestigious conferences, in an archive, in a blog post, is the methodology. The hard part is applying that methodology to solve real-world problems, to solve fascinating, interesting problems, and that requires data. That requires asking the right questions of that data, organizing that data, and labeling, selecting aspects of that data that can reveal the answers to the questions you ask. So why has this breakthrough over the past decade of the application of neural networks the ideas of neural networks. What has happened, what has changed, they've been around since the 1940s, and ideas have been percolating even before. The digitization of information, data, the ability to access data easily in a distributed fashion across the world. All kinds of problems have now a digital form that can be accessed by learning algorithms. Hardware, compute, both the Moore's law of CPU and GPU and ASICs, Google's TPU systems, hardware that enables the efficient, effective, large-scale execution of these algorithms. Community, people here, people all over the world, being able to work together, to talk to each other, to feed the fire of excitement behind machine learning. GitHub and beyond. The tooling, as we'll talk about TensorFlow, PyTorch, and everything in between that enables a person with an idea to reach a solution in less and less and less time. Higher and higher levels of abstraction empower people to solve problems in less and less time with less and less knowledge, where the idea and the data become the central point, not the effort that takes you from the idea to the solution. And there's been a lot of exciting progress, some of which we'll talk about, from face recognition to the general problem of scene understanding, image classification, to speech, text, natural language processing, transcription, translation, in medical applications and medical diagnosis, and cars, being able to solve many aspects of perception in autonomous vehicles with drivable area, lane detection, object detection, digital assistants, the ones on your phone and beyond, the ones in your home, ads, recommender systems, from Netflix to search to social, Facebook, and of course, the deep reinforcement learning successes in the playing of games, from board games to StarCraft and Dota. Let's take a step back. Deep learning is more than a set of tools to solve practical problems. Pamela McCordick said in '79, AI began with the ancient wish to forge the gods. Throughout our history, throughout our civilization, human civilization, we've dreamed about creating echoes of whatever is in this mind of ours in the machine, and creating living organisms. From the popular culture in the 1800s with Frankenstein to Ex Machina, this vision, this dream of understanding intelligence and creating intelligence has captivated all of us. And deep learning is at the core of that, because there's aspects of it, the learning aspects, that captivate our imagination about what is possible, given data and methodology, what learning to learn, and beyond, how far they can take us. And here visualized is just 3% of the neurons and 1 millionth of the synapses in our own brain. This incredible structure that's in our mind, and there's only echoes of it, small shadows of it in our artificial neural networks that we're able to create. But nevertheless, those echoes are inspiring to us. The history of neural networks on this pale blue dot of ours started quite a while ago, with summers and winters, with excitements and periods of pessimism, starting in the 40s with neural networks and the implementation of those neural networks as a perceptron in the 50s, with ideas of brand propagation, restricted Boltzmann machines, recurrent neural networks in the 70s and 80s, with convolutional neural networks, and the MNIST data set, with data sets beginning to percolate in LSTMs, bidirectional RNNs in the 90s, and the rebranding and the rebirth of neural networks under the flag of deep learning and deep belief nets in 2006, the birth of ImageNet, the data set on which the possibilities of what deep learning can bring to the world has been first illustrated in the recent years. In 2009, and AlexNet, the network that on ImageNet performed exactly that, with a few ideas like dropout that improved neural networks over time, year by year, improving the performance of neural networks. In 2014, the idea of GANs that Jan LeCun called the most exciting idea of the last 20 years, the generative adversarial networks, the ability to, with very little supervision, generate data, to generate ideas after forming representation of those, from the understanding, from the high level abstractions of what is extracted in the data, be able to generate new samples, create. The idea of being able to create as opposed to memorize is really exciting. And on the applied side, in 2014 with Deep Face, the ability to do face recognition. There's been a lot of breakthroughs on the computer vision front, that being one of them. The world was inspired, captivated in 2016 with AlphaGo and 17 with AlphaZero, beating with less and less and less effort the best players in the world at Go. The problem that for most of the history of artificial intelligence is unsolvable. And new ideas with capsule networks, and this year is the year, 2018 was the year of natural language processing. A lot of interesting breakthroughs. Google's BERT and others that we'll talk about, breakthroughs in the ability to understand language, understand speech, and everything, including generation, that's built all around that. And there's a parallel history of tooling, starting in the 60s with the perceptron and the wiring diagrams there, ending with this year with PyTorch 1.0 and TensorFlow 2.0. These really solidified, exciting, powerful ecosystems of tools that enable you to do a lot with very little effort. The sky is the limit, thanks to the tooling. So let's then, from the big picture, take into the smallest. Everything should be made as simple as possible. So let's start simple, with a little piece of code. Before we jump into the details and a big run through everything that is possible in deep learning. At the very basic level, with just a few lines of code, really 6 here, 6 little pieces of code. You can train a neural network that understands what's going on in an image. The classic that I will always love in this data set, the handwriting digits, where the input of the neural network and machine learning system is a picture of a handwritten digit, and the output is the number that's in that digit. It's as simple as, in the first step, import the library, TensorFlow. Second step, import the data set, MNIST. Third step, like Lego bricks stacked on top of each other, the neural network, layer by layer, with a hidden layer, an input layer, an output layer. Step 4, train the model, as simple as a single line, model fit. Evaluate the model in step 5 on the testing data set, and that's it. Step 6, you're ready to deploy. You're ready to predict what's in the image. It's as simple as that. And much of this code, obviously much more complicated, or much more elaborate and rich and interesting and complex, will be making available on GitHub, on our repository that accompanies these courses. Today we've released the first tutorial on driver segmentation. I encourage everybody to go through it. And then on the tooling side, in one slide, before we dive into the neural networks and deep learning, the tooling side, amongst many other things, TensorFlow is a deep learning library, an open source library from Google. The most popular one today, the most active with a large ecosystem. It's not just something you import in Python and to solve some basic problems. There's an entire ecosystem of tooling. There's different levels of APIs. Much of what we'll do in this course will be the highest level API with Keras. But there's also the ability to run in the browser, TensorFlow.js, on the phone, with TensorFlow Lite, in the cloud, without any need to have a computer, hardware, anything, any of the libraries set up on your own machine. You can run all the code that we're providing in the cloud with Google Collaboratory, and the optimized ASICs hardware that Google is optimized for TensorFlow with their TPU, Tensor Processing Unit, the ability to visualize tensor board models that provide in TensorFlow. And there's just an entire ecosystem, including, most importantly, I think, documentation and blogs that make it extremely accessible to understand the fundamentals of the tooling that allow you to solve the problems, from natural language processing to computer vision to GANs, generative adversarial neural networks, and everything in between, reinforcement learning, and so on. So that's why we're excited to sort of work both in the theory in this course, in this series of lectures, and in the tooling and the applied side of TensorFlow. It really makes it these ideas exceptionally accessible. So, deep learning at the core is the ability to form higher and higher level abstractions of representations in data, in raw patterns, higher and higher levels of understanding of patterns. And those representations are extremely important and effective for being able to interpret data. Under certain representations, data is trivial to understand. Cat versus dog, blue dot versus green triangle. Under others, it's much more difficult. In this task, drawing a line under polar coordinates is trivial. Under Cartesian coordinates, it's very difficult and, well, impossible to do accurately. And that's a trivial example of representation. So our task in deep learning, with machine learning in general, is forming representations that map the topology, whatever the topology, the rich space of the problem that you're trying to deal with, of the raw inputs, map it in such a way that the final representation is trivial to work with, trivial to classify, trivial to perform regression, trivial to generate new samples of that data. And that representation, higher and higher levels of representation, is really the dream of artificial intelligence. That is what understanding is. Making the complex simple, like Einstein back in 2000 said. And that, with Jürgen Schmidhuber and whoever else said it, I don't know, that's been the dream of all of science in general. Of the history of science is the history of compression progress, of forming simpler and simpler representations of ideas. The models of the universe, of our solar system, with the Earth at the center of it, is much more complex to do physics on than a model where the sun is at the center. Those higher and higher levels of simple representations enable us to do extremely powerful things. That has been the dream of science and the dream of artificial intelligence. And why deep learning? What is so special about deep learning in the grander world of machine learning and artificial intelligence? It's the ability to more and more remove the input of human experts, remove the human from the picture, the human costly, inefficient effort of human beings from the picture. Deep learning automates much of the extraction from the raw, gets us closer and closer to the raw data without the need of human involvement, human expert involvement. Ability to form representations of the raw data, as opposed to having a human being need to extract features, as was done in the 80s and 90s and the early aughts to extract features with which then the machine learning algorithms can work with. The automated extraction of features enables us to work with larger and larger data sets, removing the human completely, except from the supervision labeling step at the very end. It doesn't require the human expert. But at the same time, there is limits to our technologies. There's always a balance between excitement and disillusionment. The Gartner hype cycle, as much as we don't like to think about it, applies to almost every single technology. Of course, the magnitude of the peaks and the drops is different. But I would say we're at the peak of inflated expectation in deep learning. And that's something we have to think about as we talk about some of the ideas and exciting possibilities of the future. And with self-driving cars that we'll talk about in the future lectures in this course, we're at the same. In fact, we're a little bit beyond the peak. And so it's up to us, this is MIT, and the engineers, and the people working on this in the world, to carry us through the drought, to carry us through the future as the ups and downs of the excitement progresses forward into the plateau of productivity. Why else not deep learning? If we look at real-world applications, especially with humanoid robotics, robotic manipulation, and even, yes, autonomous vehicles. The majority of the aspects of autonomous vehicles do not involve, to an extensive amount, machine learning to date. The problems are not formulated as data-driven learning. Instead, they're model-based optimization methods that don't learn from data over time. And then from the speakers that these couple of weeks, we'll get to see how much machine learning is starting to creep in. But the examples shown here with the amazing humanoid robotics from Boston Dynamics, to date, almost no machine learning has been used except for trivial perception. The same with autonomous vehicles. Almost no machine learning and deep learning has been used except with perception. Some aspect of enhanced perception from the visual texture information. Plus, what's starting to be used a little bit more is the use of recurrent neural networks to predict the future. Predict the intent of different players in the scene in order to anticipate what the future is. And these are very early steps. Most of the success that you see today, the 10 million miles that Waymo's achieved, has been attributed mostly to non-machine learning methods. Why else not deep learning? Here's a really clean example of unintended consequences. Of ethical issues we have to really think about. When an algorithm learns from data based on an objective function, a loss function, the consequences of an algorithm that optimizes that function is not always obvious. Here's an example of a human player playing the game of Coast Runners with it's a boat racing game where the task is to go around the racetrack and try to win the race, and the objective is to get as many points as possible. There are 3 ways to get points: the finishing time, how long it takes you to finish, the finishing position, where you were in the ranking, and picking up quote-unquote turbos, those little green things along the way. They give you points. Okay, simple enough. So we design an agent, in this case an RL agent, that optimizes for the rewards. And what we find on the right here, the agent discovers that the optimal actually has nothing to do with finishing the race or the ranking. They can get much more points by just focusing on the turbos and collecting those little green dots, because they regenerate. So you go in circles over and over and over, slamming into the wall, collecting the green turbos. Now that's a very clear example of a well-reasoned a formulated objective function that has totally unexpected consequences, at least without sort of considering those consequences ahead of time. And so that shows the need for AI safety for a human in the loop machine learning. That's why not deep learning exclusively. The challenge of deep learning algorithms, of deep learning applied, is to ask the right question and understand what the answers mean. You have to take a step back and look at the difference, the distinction, the levels, degrees of what the algorithm is accomplishing. For example, image classification is not necessarily scene understanding. In fact, it's very far from scene understanding. Classification may be very far from understanding. And the data sets can vary drastically across the different benchmarks in the data sets used. The professionally done photographs versus synthetically generated images versus real world data. And the real world data is where the big impact is. So oftentimes the one doesn't transfer to the other. That's the challenge of deep learning. Solving all of these problems of different lighting variations, pose variation, interclass variation, all the things that we take for granted as human beings with our incredible perception system, all have to be solved in order to gain greater and greater understanding of a scene. And all the other things we have to close the gap on that we're not even close to yet. Here's an image from the Andre Carpati blog from a few years ago of former President Obama stepping on a scale. We can classify, we can do semantic segmentation of the scene, we can do object detection, we can do a little bit of 3D reconstruction from a video version of the scene. But what we can't do well is all the things we take for granted. We can't tell the images in the mirrors versus in reality is different. We can't deal with the sparsity of information. Just a few pixels on President Obama's face, you can still identify him as the president. The 3D structure of the scene, that there's a foot on top of a scale, that there's human beings behind a single image, things we can trivially do using all the common sense semantic knowledge that we have. We cannot do the physics of the scene, that there's gravity, and the biggest thing, the hardest thing, is what's on people's minds. And what's on people's minds about what's on other people's minds, and so on. Mental models of the world, being able to infer what people are thinking about. Being able to infer, there's been a lot of exciting work here at MIT about what people are looking at. But we're not even close to solving that problem either. But what they're thinking about, we haven't even begun to really think about that problem, and we do it trivially as human beings. And I think at the core of that, I think I'm harboring on the visual perception problem, because it's one we take really for granted as human beings, especially when we're trying to solve real-world problems, especially when we're trying to solve autonomous driving, is we have 540 million years of data for visual perception, so we take it for granted. We don't realize how difficult it is. And we kind of focus all our attention on this recent development of 100,000 years of abstract thought, being able to play chess, being able to reason. But the visual perception is nevertheless extremely difficult. At every single layer of what's required to perceive, interpret, and understand the fundamentals of the scene. And a trivial way to show that is just all the ways you can mess with these image classification systems by adding a little bit of noise. The last few years, there's been a lot of papers, a lot of work to show that you can mess with these systems by adding noise. Here, 99% accuracy predict a dog, add a little bit of distortion. Immediately the system predicts with 99% accuracy that it's an ostrich. And you can do that kind of manipulation with just a single pixel. So that's just a clean way to show the gap between image classification on an artificial data set like ImageNet and real-world perception that has to be strong, especially for life-critical situations like autonomous driving. I really like this Max Tegmark's visualization of this rising sea of the landscape of human competence from Hans Marmot. And This is the difference as we progress forward and we discuss some of these machine learning methods, is there is the human intelligence, the general human intelligence, let's call Einstein here, that's able to generalize over all kinds of processes, over all kinds of, from the common sense to the incredibly complex. And then there is the way we've been doing, especially data-driven machine learning, which is savants, which is specialized intelligence, extremely smart in a particular task, but not being able to transfer except in the very narrow neighborhood on this little landscape of different, of arts, cinematography, book writing at the peaks, and chess, arithmetic, and theorem proving and vision at the bottom. There's this rising sea as we solve problem after problem. The question, can methodology and the approach of deep learning of everything we're doing now keep the sea rising? Or do fundamental breakthroughs have to happen in order to generalize and solve these problems? And so from the specialized, where the successes are, the systems are essentially boiled down to, given a data set, and given the ground truth for that data set, here's the apartment cost in the Boston area, be able to input several parameters, and based on those parameters, predict the apartment cost. That's the basic premise, approach behind the successful supervised deep learning systems today. If you have good enough data, has good enough ground truth, and can be formalized, we can solve it. Some of the recent problems that we will do an entire series of lectures in the third week on deep reinforcement learning showed that from raw sensory information with very little annotation, through self-play, where their systems learn without human supervision, are able to perform extremely well in these constrained contexts. The question of a video game. Here, Pong to Pixels, being able to perceive the raw pixels of this Pong game as raw input and learn the fundamental, quote-unquote, physics of this game. Understand how it is this game behaves and how to be able to win this game. That's kind of a step toward general purpose artificial intelligence. But it is a very small step because it's in a simulated, very trivial situation. That's the challenge that's before us. With less and less human supervision, be able to solve huge real-world problems. From the top, supervised learning, where majority of the teaching is done by human beings throughout the annotation process, the labeling all the data by showing different examples. And further down to semi-supervised learning, reinforcement learning, and supervised learning, removing the teacher from the picture and making that teacher extremely efficient when it's needed. Of course, data augmentation is one way, as we'll talk about. So taking a small number of examples and messing with that set of examples, augmenting that set of examples through trivial and through complex methods of cropping, stretching, shifting, and so on, including through generative networks, modifying those images to grow a small data set into a large one, to minimize, to decrease further and further the input that the human is, the input of the human teacher. But still, that's quite far away from the incredibly efficient both teaching and learning that humans do. This is a video, and there's many of them online for the first time, a human baby walking. We learn to do this, you know, it's one-shot learning. One day you're on all fours, and the next day you put your two hands up, and then you figure out the rest. One shot. Well, you kind of play around with it. But the point is, you're extremely efficient. With only a few examples, are able to learn the fundamental aspect of how to solve a problem. Machines, in most cases, need thousands, millions, sometimes more examples, depending on the life-critical nature of the application.
因为你讲你输入就这么多，你再进去是有问题。
The data flow
那这个
of
我有听到这个 EODH， 它其实就是
supervised learning systems is there's input data, there's a learning system, and there is output. Now, in the training stage for the output, we have the ground truth, and so we use that ground truth to teach the system. In the testing stage, when it goes out into the wild, there's new input data over which we have to generalize the learning system and we have to make our best guess. In the training stage, the process is with neural networks is given the input data for which we have the ground truth, pass it through the model, get the prediction, and given that we have the ground truth, we can compare the prediction to the ground truth, look at the error, and based on that error, adjust the weights. The types of predictions we can make is regression and classification. Regression is a continuous, classification is categorical. Here, if we look at weather, the regression problem says what is the temperature going to be tomorrow, and the classification formulation of that problem says is it going to be hot or cold, some threshold definition of what hot or cold is. That's regression classification. On the classification front, it can be multi-class, which is the standard formulation where you're tasked with saying there's only a particular entity can only be one thing, and then there's multi-label where a particular entity can be multiple things. And overall, the input to the system can be not just a single sample of the particular data set, and the output doesn't have to be a particular sample of the ground truth data set. It can be a sequence to sequence, a single sample to a sequence to a sample, and so on. From video captioning, where it's video captioning, to translation, to natural language generation, to, of course, the one-to-one general computer vision. Okay, that's the bigger picture. Let's step back from the big to the small, to a single neuron, inspired by our own brain, the biological neural networks in our brain, and the computational block that is behind a lot of the intelligence in our mind. The artificial neuron has inputs with weights on them, plus a bias, an activation function, and an output. It's inspired by this thing. As I showed it before, here visualizes the thalamocortical system with 3 million neurons and 476 million synapses. The full brain has 100 billion neurons and 1,000 trillion synapses. ResNet and some of the other state-of-the-art networks have in the tens, hundreds of millions of edges of synapses.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in